Yeah, please go ahead, John.
Thanks, guys. So I'm John Mellor Crummey, a professor of computer science in Rice University, and my group is developing the HPCToolkit performance tools. And so we started this project a long time ago, perhaps about 20 years ago, and we're currently working on adapting HPCToolkit to support performance analysis on the forthcoming GPU-accelerated exascale supercomputers. And so while HPCToolkit can be used on CPUs as well as GPUs, the focus of most of my talk today is going to be on the GPU capabilities. So on the title slide, I wanted to mention that there's a set of examples that can be downloaded and run and measured and analyzed on Ascent. And there's also one example to try on Theta GPUs. So I said the focus was on GPUs, and so these are GPU-based examples for most of them. So the overview of the HPCToolkit project is that we're developing tools to measure, analyze, attribute, and understand performance of applications, libraries, tools, and system software on extreme scale parallel systems. So we use HPCToolkit in our own work to analyze our own tools and improve their performance and their parallelism. So it's not just for applications, and you can also use it to analyze the performance of libraries if that's what you're working on, or frameworks. So as part of the project, we're developing new strategies and mechanisms to measure and analyze the performance and also resource utilization of GPU accelerated compute nodes. And we're also trying to lead the evolution of hardware and the software ecosystems for better tools. And in doing that, we've been engaged with NVIDIA and Intel and AMD for quite a while. And some of the things that they're putting out in their hardware are in part based on requests from us. So I have a team of people at Rice University. I've got 4 staff members and some grad students. And we also work very closely with Bart Miller's group at the University of Wisconsin. And the whole project is mostly funded by the DOE Exascale Computing Project, but we also have some funding from Argonne, the NNSA, Tri-Labs, AMD, and Intel. So I'm sure that you've touched upon this a little bit in the course of the day, but I just wanted to refresh a little bit. So when you're analyzing performance on modern supercomputers, there's many different concerns. So you're concerned about the compute performance on the CPU and GPU. You're concerned about the data movement costs within and between memory spaces. Memory copies are very costly, especially when they're going between, say, CPU memory and GPU memory. You're also concerned about communication and I/O and the extent to which these slow down your entire application. So there's lots of different ways that you can hurt performance. There's insufficient parallelism and load imbalance and serialization, replicated work, and parallel overhead. And the hardware and execution model is very complex. So we've got multiple compute engines with different characteristics. So we've got CPUs and then GPUs on these GPU accelerated systems. About 95% or more of the computational performance is going to come from the GPUs. And so we have to be very concerned about the performance of our code on accelerators. There's also multiple memory spaces with different performance characteristics. The CPU and GPU have their own individual memory hierarchies that have their own quirks. And there's often a very large gap between the programming model and the implementation. So for instance, in OpenMP, you can write a little offloading directive just as a comment in your code, and then the compiler will tear pieces out of your procedures and map it onto a different device and insert data copies back and forth. We have similar kinds of gap between the programming model and the realization on the hardware for the template-based programming models such as Raja and Cocos, which I'm sure that you've touched upon in the course of ATPESC. So another complicating thing is that you have asynchronous execution. And so this is particularly true with GPUs, where it's very common to offload a kernel and just you initiate it, and then you go on to do something else on the CPU while the kernel executes on the GPU. So let me tell you a little bit about HPCToolkit, and then I'll tell you a little bit about understanding the performance of parallel programs using HPCToolkit's GUIs. I mentioned the code-centric and time-centric views. we get a chance to play with these during the hands-on session. And so I'm not going to show a live demo here. We can take that offline for the hands-on session. And then I'll talk about monitoring GPU accelerated applications and some work in progress. So to start, HPCToolkit is monitoring applications at a very low level. So it employs binary level measurement analysis. So it's observing executions of fully optimized, dynamically linked applications, and it's observing the code both on the CPU and GPU. Supports multilingual codes. So if you have a mix of Fortran, C++, C, even binary libraries that come from third parties. So for instance, NVIDIA's CUDA runtime, math libraries, and whatever's running on the system. So on the CPU, HPCToolkit collects measurements by sampling. So it periodically is interrupting the application and then asking where the application is. And so what I mean by asking where it is, we're looking at the call stack to find out that I was in a routine C when called from B, when called from A, when called from main. And so every time we get an interrupt for a timer or a hardware performance counter, we attribute those costs to the full calling context in which they're incurred. And similarly, when you're offloading code to GPUs, we attribute the cost to where you offloaded the computation to the GPU, a heterogeneous call stack that includes both CPU and GPU procedure frames. So for GPU performance, we're measuring that using APIs that are provided by the vendors. So typically we're using callbacks to monitor the launch of and completion of GPU operations. And there's an activity API that's provided by NVIDIA and by AMD to monitor and present information about asynchronous operations on GPU devices. So they provide us with a trace and say, operation started at time T and ended at time T plus delta. And then we can take that information and incorporate it into a profile or produce a trace. On NVIDIA GPUs, there's also support for PC sampling for fine-grained performance measurement. This is particularly important when all of the computation cost is going to be offloaded on GPUs. If all you know is that a kernel is running and you have no idea what it's doing inside the kernel, you don't have any idea whether whether particular parts of the code are very costly or whether your memory access patterns are very inefficient. And so you really need some fine-grained detail in order to be able to tune up the GPU code. So HPCToolkit enables you to associate metrics with both static context like procedures and source lines and loop nests, and also dynamic context, full call chains. And so the contexts include loop nests, procedures, inline code, and calling context on both the CPU and the GPU. Now, with HPCToolkit, you can also specify and compute derived and CPU and GPU metrics of your choosing. So with an Excel-like spreadsheet-like notation, you can compute your own metrics from other metrics. So for instance, if you have measures of time, you can also compute measures of waste and scalability loss. Or from cache misses and cache accesses, you can compute things like cache miss rates if you're worried about your memory hierarchy performance. So finally, HPCToolkit supports top-down performance analysis where you can identify the things that are of interest and then drill down to the causes, moving up and down call chains, and also looking at the execution flow over time. So here's the workflow for HPCToolkit. So you start by compiling and linking your code the way you normally would. And so we don't require that you modify your makefiles in any way, shape, or form. The only thing that we suggest is that you add a -G to the host compiler. You can add -G even with optimization. And this is something that tells the compiler to include line map information in your binary, because otherwise all we can do is correlate the cost to procedures. But if you want to correlate it to individual source lines, then you have to tell the compiler to add the line map information. And that's what -G does. And then on the GPUs, there's also another option. And so on NVIDIA GPUs, there's a -line info. And so every GPU vendor has something different that you have to worry about. So augmenting your makefile to just say collect line level information, have the compiler collect the line map information is good practice for getting ready for performance analysis. So when you launch your application, you launch it with our HPC run launcher. So if you're launching an MPI program, let's say you were using something like MPI run to launch it, you would say MPI run, HPC run your application. You just sort of insert it between the MPI and your application as it launches. And then what HPC run will do is it'll preload our measurement subsystem into your application address space, and it'll collect profiles of your code as it runs on CPUs and GPUs. And so in addition to the profiles, it can also optionally collect traces if you'd like. And then as the program runs, it's going to actually record GPU binaries that are loaded into the GPU and launched. Some of the binaries may only be JIT compiled at runtime. Other binaries are tucked away inside your host binary, but for instance, NVIDIA won't release their fat binary format, and so we can't effectively get them out until we use a tooling interface at runtime to extract them. So we'll just record the binaries on disk for later post-processing. So the way that you use HPC run, so this is just assuming that first we're talking here about just profiling something on a GPU. So you can say HPC run -E. This is saying this is the event, and I specify a GPU and I specify a GPU kind. And so the GPU can be either NVIDIA, AMD, or OpenCL, which is a vendor independent, or Level 0, which is an Intel runtime. And so we may change the names of these in the future to be a little bit more intuitive. So you can also trace activities on a GPU. Right now, we don't support tracing for Level 0, but we support tracing for all of the other GPU interfaces. If you want to do PC sampling, which is only supported on NVIDIA GPUs, you just add this comma PC after saying that you want to measure it on NVIDIA GPUs. And here we're adding a trace option as well. So if you want to profile on both the CPU and the GPU, you can say I want to profile with real time on the CPU, and I also want to monitor the GPU. And so this will do both profiling and tracing of the CPU and the GPU. And then if you're using this with a job launcher for a parallel application, you might use JS run or S run or AP run to launch your application. And so you specify all of your parameters for the job launch, then you specify HPC run, and then your app at the end. And then in between, you can put in some arguments to say what you want to monitor. So the way HPCToolkit fits in with the software stacks is that on NVIDIA GPUs, we have like Raja and Cocos can either sit on top of OpenCL or they can sit on top of CUDA. Then NVIDIA has this CUPTI, this CUDA Performance Tools interface that can monitor CUPTI. And then HPCToolkit uses CUPTI to monitor your application. It can also add instrumentation with this sanitizer API that's provided by NVIDIA. And so we're really interposing this measurement substrate between the GPU software stack and the physical device. And then it's similar on Intel GPUs and on AMD GPUs. So for measuring GPU accelerated applications, there's a couple of different measurement interfaces. So on the CPU, we get to use a hardware performance monitoring unit. And so we can say, interrupt a thread after 1 million cache misses, or there's about several hundred events on typical processors. And so you can choose to monitor instructions or monitor various aspects of the memory hierarchy, misses at different levels, misses in something called the translation look-aside buffer, which is showing translations for pages of virtual memory. And on the GPU, we have both hardware counters, which are counting events like cache misses and execution of floating point instructions. And then on NVIDIA GPUs, we also have support for PC sampling. And so what the PC sampling does is it's a very low level way of monitoring things at an instruction level on the GPU. And so it will sample the instructions and it will let us know whether the sampled instruction, whether the GPU is stalled or not. And if it's stalled, it'll tell us it's stalled waiting for memory, or it's stalled waiting for a dependence on a prior instruction. So there's about a dozen stall reasons that NVIDIA GPUs can record. And then there's some software measurement interfaces that we use. So we use glibc's LD audit to track the dynamic loading of shared libraries. We use the Linux perf events interface for measuring inside the CPU kernel. And so not only do we see the application, but if the permissions are set properly, then we can also see what's going on in the kernel. So things like allocating pages and clearing pages and things like that. You'd be surprised actually how much time gets spent in the kernel sort of thrashing on memory. And then there's a GPU monitoring and instrumentation libraries that are supplied by each of the vendors. So we don't get to really interact directly with the GPUs. We can only use the APIs that the vendors supply. So there's several different measurement modalities and interfaces. So we're using sampling on the CPU. We're using callbacks when the GPU operations are launched and sometimes when they're completed. And there's a GPU event stream, which includes timings for memory copies and kernels and synchronization operations. And also on NVIDIA GPUs, it includes a stream of PC samples that provide us some very detailed information about what's actually going on. So that's how we collect our profile data and we collect our traces, is that we just turn on HPC Run injects our measurement infrastructure into your application. And with the command line switches, it'll tell it what to record. And so now we've got a bunch of data and we need to figure out how to interpret it. So all of the data is recorded at the level of individual machine instructions. And so we know the address of machine instructions, and we also know where your code was loaded. And so we use this utility that we built called HPCToolkit, which will analyze CPU and GPU binaries to recover the program structure. So we look at the machine code and figure out how it maps to source lines. We also build a control flow graph inside the machine code to figure out where loop nests are. And so we identify what code is inside loops. We also look at other information like inlining information provided by the compiler. And so we can assemble all of that into a heterogeneous call stack that spans the CPU and GPU and has things like procedures and loop nests and inline code and statements. You'll see a little bit more about that in a minute. So HPCToolkit is pretty simple to use. You can say HPCToolkit and you just invoke it on your application, and it will yield the file yourappname.hpcstruct. And this is basically just looking through the binary and all the information that the compiler has put in it, and also the control structure of the machine code to figure out what code is in loops, what code is not in loops, where was code inlined, things like that, so that we can use that to interpret the measurement data. So if your application is very big and HPCToolkit takes a long time, we've worked pretty hard over the last couple of years to add a lot of multi-threading. So you can say like -J16 and use 16 threads to analyze your code, and it gets a lot faster. So we also analyze the GPU binaries that are recorded by HPC Run. So I mentioned that as you run your application, when code gets loaded into the GPU, we record these GPU binaries on the fly. They get recorded in the measurements directory. And so then you just invoke HPCToolkit and you point it at the measurements directory, and it will analyze all the GPU binaries that were recorded inside. You can also use parallelism for this by specifying a number of threads. And then there's an expensive option, GPU CFG, which says compute control flow graphs and loop nests in the GPU binaries. And this is in part expensive because we don't actually have a good interface to get this information from NVIDIA GPUs. We have to actually depend upon NVIDIA's tools, and in a way that is rather slow. So this is something that should be done when you're really interested, but it shouldn't be done all the time. And certainly if you're not collecting PC sampling information, then there's no point in having the GPU CFG, because if you're only measuring things at the level of individual kernel launches, then there's no line level detail or statement level detail at all. So then the next thing we do, so now we have our profile and traces, and we have our program structure information that was recorded by HPCToolkit. So we have two utilities, HPCProf, which will take the structure information and the profiles and the traces and correlate all the measurements with the source code. Now, if you have a large application that was running on say, thousands of threads, then you wouldn't want to analyze that data on a head node sequentially. HPCProf is a sequential program. HPCProf MPI is a version of HPCProf that's been parallelized with MPI. And so this runs in parallel, and it can analyze measurement data a lot quicker by using an MPI program, and every MPI rank will analyze some of the data. So in order to use HPCProf, you just say HPCProf and say -s to pass in a structure file, and then you pass in a measurements directory. And so then it'll analyze everything in the measurements directory, and it'll use the program structure information. Now, you might have program structure for your application. You might have also computed it for a library of interest. You can specify many different -s options and HPC struct files for as many libraries as you care about. If you don't actually specify the program structure, then it won't map to loop nests or inline code, but you'll still see measurements at the procedure level and the line level. Now, if you want to do this with HPCProf MPI, if you've collected a lot of data, then you can just launch with your favorite job launcher, whether it's srun or jsrun or qsub. You can launch HPCProf MPI, and you pass it the same sort of arguments. You pass it structure files, and you pass it a measurements directory, and it'll analyze all the stuff in the measurements directory and correlate it with the source code as according to the program structure files. So then the last step is we have an interactive user interface for exploring the data. And so what this can do for a GPU accelerated program is it has a source pane, and then it has a navigation pane, which in this case, we're looking at a top-down view. And so this is showing a call stack. In this case, the call stack starts on the CPU, and then it's going into the GPU. And then there's actually some detail in the GPU as well. And I'll say a little bit more about that in a minute. Now, when we're doing this for a parallel program, what we do is we add together the profiles of every thread and every GPU stream, because what you want to know is where you spent your time in your code. If you want to know something about execution dynamics, then you'll use the trace view that I'll show you in a minute. So here we have a call stack that starts on the CPU and then enters the GPU. And we have CPU metrics, we have coarse grain GPU metrics. By coarse grain metrics, I mean like at the operation level, like memory copies or kernel executions. Then there's fine grain metrics such as instruction counts. And so we can associate that with individual source lines and loops and inline code inside the GPU when you're using PC sampling on NVIDIA GPUs. And then we also get derived metrics that will tell us about GPU utilization inside the kernels. So here's an example of coarse and fine grain measurements on NVIDIA GPUs. So we have CPU time, we have GPU instruction counts, and we also have GPU instruction stall counts. And so this column is showing stalls for any reason, but there's actually about a dozen other columns that tell you whether you're stalled waiting for an instruction fetch or values from memory or execution dependencies or whatnot. But the part that we're really proud of is the detail inside GPU kernels. So HPCToolkit does something that no other tool does. So what you can see here is this is launching a GPU kernel called cycle tracking kernel. So this is from the Quicksilver code. You can actually run these measurements yourself with the example that I've put on Theta GPU. So here the GPU kernel is cycle tracking kernel. And so this is calling cycle tracking guts, which calls collision event, which calls macroscopic cross section. And then we can see that in this cycle tracking guts, there's a loop, and then collision event is called inside the cycle tracking loop. And then there's a couple of loops in collision event and then there's some inline code in here. And so we recover all of this information post-mortem. So what we're actually collecting on the GPU is flat PC samples. And what HPCToolkit does is it reconstructs an approximate call and context tree from these flat samples by understanding the static call graph, where calls are in the code, and then it uses sampling to see how many times it observes each call. And then for every function, if it's called from multiple places, then we split up the cost for the function according to the call counts from each invocation. And so then this is something that gives us a lot of detail inside the GPU kernels. And this is important if you actually have complex GPU kernels. So in fact, the Mercury code at Lawrence Livermore has about 100,000 lines inside its kernel. And so if you just told them the kernel is slow, that's not a really good diagnostic. So having this more detailed information is useful. So we can also do this on Intel GPUs. We can measure the time spent in each kernel. We can measure instruction counts. So in this case, we're measuring it with instrumentation using a tool called GTPin, which will add instrumentation to basic blocks inside the GPU code. And then we can also monitor memory copies. We can monitor the copies that are going to and from the device and the amount of bytes that are copied in each direction. And so this applies to software like the DPC++ programming model. And we collected this data using one of the one API versions on top of the OpenCL runtime. So there's also some work on level 0 by our group, but that's not as mature as the work on top of the OpenCL runtime so far. So for DPC++, you can actually use either runtime. So it's your choice. So we can also do the same kind of thing for AMD GPUs. We can get CPU time, GPU kernel time, copy time, synchronization time, copy counts, but no fine-grained measurements. There's just no support for fine-grained measurements, either by instrumentation or hardware support for instructional level measurements at present. So we also can measure things like OpenMP programs, and we can reconstruct the call stack where you can see that there's an outline function where there was an OpenMP pragma that's offloading code to the GPU, and we get to see that this code has been offloaded, and then it's executing and it's offloading the code onto the GPU here. So here's where it starts, and then this is what's happening inside the offloaded code, and then this is where the kernel actually ends up on the GPU. So for understanding, so far I've showed you profiles, but for understanding temporal behavior, the profiles compress out the time dimension. So what we do is we trace a series of samples for every thread that's running on the CPUs. And so when we unwind the call stack, we take a sample in C, one call from B, one call from A, one call from main, and we do that at time t and time t plus delta and time t plus 2 delta. And we do this for every thread across the whole machine. And so we visualize this at different levels. So if you take this visibility plane and you pull it all the way up to the top, you would see that everybody is in the blue routine, say that's main. And then as we start sliding this down, we're revealing lower levels of detail. So maybe main is calling some initialization phase. And then the initialization phase has two parts. It has the yellow part followed by the purple part. And so these colors each represent procedures. And so you'll see a little bit more about that in just a minute. So here is a trace view of on 22 nodes of Power 9 with each with 6 NVIDIA V100s. So we have 128 MPI ranks and 640 GPU streams. Looks like a little bit of a mess here. So what we have is we have threads and GPU streams on the vertical axis, and then time flows horizontally. And so it's a little bit easier to see if we zoom in. So I'll do that in just a second. But for every point in time, so here's a cursor that's pointing at a particular thread. So it's looking at something that's running on a particular node in rank 9 GPU stream 1 in a particular GPU context. And it will tell us the full calling context of that piece of work that is executing at that point in time on this MPI rank. So now if we zoom in a little bit, yes, is there a question?
So we have 5 minutes.
Yep, I understand. Thank you. So let's zoom in and look at a little portion of the trace closer. So this white pane represents the entire space of the trace, like across the threads, and then time on this dimension. And so now we're just going to focus on a few threads for a shorter fraction of time. So now when you zoom in, actually you can start to see some logical organization. You see this sort of staircasing here, and this green routine actually represents GPU synchronization. And so all of a sudden you can see temporal patterns and relationships between the threads that repeat over time. And so what's happening with the set of GPU streams on one MPI rank is also happening on another MPI rank. So we've got some trace lines here that represent CPU threads, and we've got other trace lines that represent the GPU streams on that node. And so you get a chance to play around with this interface, and you can zoom and pan. And the most important thing is to go in and look at it in detail and hone in on a particular iteration in an iterative code and say, let me look at a couple of representative iterations. And then you can find out something about how the threads, whether there's load balance or whether they're spending a lot of time waiting for IO or whatnot. So the GPU monitoring capabilities of HPCToolkit, we have significant support in our master branch for NVIDIA. And so that's what you'll get a chance to play with today if you want to try this in the hands-on session. And so it's measuring GPU kernels, kernel launches, memory copies, and synchronization using callbacks in the activity API. It also has instruction level support for performance measuring using PC sampling, as I mentioned several times. AMD and Intel GPUs, we're also using callback APIs. And I have permission, this is approved for public release, that right now we're using GTPin, but in the future, Intel's GPUs are going to support instruction level measurement of GPU code. I can't say much more about that. They've approved this phrase, but I can't say much more. I can't tell you about their hardware. And AMD has actually told us a little bit less. I'm not allowed to say anything about their hardware, but on GitHub, they've committed code that shows PC sampling, support for PC sampling of GPU code. So I can't say anything about their hardware, but I can say that I've seen PC sampling support in their code on GitHub. So you do the judgment, okay? So some work in progress. So we're working on enhancing support for Intel, AMD, and NVIDIA GPUs. So one of the things that you'll see is that we've done some new work on interpreting inlining information that's available in the GPU binaries that is available since CUDA 11.2. So if you try this on Theta GPU, you'll actually see all of this in the Quicksilver example. And we're working on reducing the fine-grained measurement overhead with low overhead PC sampling. We've been collaborating with NVIDIA, and as of CUDA 11.3, they now have a new API for PC sampling that we're working with. We're working on enhancing the scalability of HPCToolkit, improving the user interface to make it easier to get information out of it, and then working on making this thing reliable and generate measurements everywhere for complex applications. So finally, I just wanted to say that the work that we're doing is not in a vacuum. In fact, we're involved in a lot of other work. So we're working with the GPU vendors on presenting needs for hardware support for fine-grained measurement. We're working with Red Hat on glibc to address some shortcomings in the LD audit interface. Working with the GPU vendors on their software stacks. Working with LLVM on dwarf information, working with the OpenMP community to define the OpenMP tools interface, and our partners at the University of Wisconsin who are working on binary analysis. When I say they're working on it, we're working on it as well. Okay, so that's about what I had. I'd be happy to answer a couple of brief questions, and then we can take anything else to the hands-on session.